Hey everybody, hope you're all having a good day. Welcome back to the next video tutorial for Forecast Forge. I'm going to start where we left off last time. With the same data, we've got our daily sessions data, and then we used the Forge forecast custom function to make a forecast. So this week I'm going to show you a similar way to do the same thing. Some of you might prefer it. It is better in some ways and worse in other ways. We'll get into that. Okay, so we're going to make the same forecast but using the sidebar. Okay, so these fields over here, we need to fill them in the same way as we filled in the custom function. So we've got A2 to A1690, B2 to B1325, no regressors, and the country is the UK. Let's give it a bit of space. And okay, off we go. So calling from the sidebar, we don't have the same 30-second timeout that we have when we use the custom function. So it does a little bit extra, which we'll get into later on. But it's mostly the same, and a lot of the extra stuff happens in parallel, so it shouldn't take that much longer. Okay, there we go. So we've got our forecast results here. Our expected values are the same, and then you'll notice that the predictive intervals are slightly different between the two forecasts. That's because of the algorithm used to come up with the predictive intervals is a Monte Carlo simulation, so the results will end up slightly different each time. I could use a different algorithm that wouldn't have so much variance in the output, but it would also be a lot slower. And particularly over here, we need to finish everything within 30 seconds to prevent the custom function timeout. If you're running into problems where these values are different enough that affects the business decision that you're making, then please get in touch with me and I'll see what I can do to help you out. Okay, so because we've used the sidebar, we get this extra information back about how good the forecast is. We've got this little table of results. Now let me just explain quickly how that is calculated. So here we've got data going back to early 2017, and we're forecasting a year into the future. So we've got let's make this red. We've got our data, and then we are wanting to forecast what happens out here. So what the sidebar does is it might take the data up to here and then forecast this bit, and then we can compare how good we are, how good the forecast results are against what actually happens. And then, well, in this case, we can see here it says we've used two folds. Folds is a statistical term in cross-validation, which means that we've done this, and then we've also maybe taken the data as far as here, and again predicted a year into the future, so that'll be about there, and then again we can compare. So that means that if our actual data had some like really weird oddity in it here, we'd get more reliable estimates from our validation. And then we can see the results of that in this table, which is 4 rows by 4 rows. Now 4 rows by 4 columns. Now each column is a different way of calculating the error, and each row is a different aggregate. So let's ignore the 730 and 365 rows for now and think just about the 1 day row. So what that does is for each day it calculates the difference between the forecast value and the actual value. So the mean error is just the mean of all those values. The mean absolute error is the mean of the absolute value. The absolute value makes everything positive. So the difference between those two is, let me clear all this. If we have our actual values and we have our forecast values, so we can see here that sometimes the forecast is below, sometimes it's above, sometimes it's below, sometimes it's above. So here the error is negative, and here the error is positive. When we find the mean of all that, those positives and negative ones cancel each other out. So what the mean error tells us is whether the forecast tends to overestimate or whether it tends to underestimate the true value. Whereas with the absolute error, all the errors are positive. So we get we get a truer picture of what's going on here. They don't cancel each other out in the same way. Rmse stands for root mean squared error. So when you square a negative number, you get a positive number. So that's another way of making sure that the errors can't cancel out. And in addition to that, the squaring makes bigger errors worse. For example, if you have an error of 2, it squares to 4. But if you have an error of 4, it squares to 16, which is 8 times bigger than the error we had with 2. So this metric penalizes big errors a lot more than it does small errors. This is used a lot in machine learning because it's continuous and differentiable, which is important for things like gradient descent, and also because it's theoretically linked with normally distributed errors, which is a big assumption when you do things like linear regression. Finally, we have the fourth one, which is the MAPE, which stands for mean absolute percentage error. So you'll notice that these ones are all percentages. That's just a scale-free way of saying how big the error is. You can click this link here and read more about all these different types of errors. Okay, so that's the columns. Let's think about the rows. So we know what it is for daily. We calculate the error for each day. But for a lot of business forecasts, the daily error, it doesn't really matter that much because people aren't, particularly if you're forecasting for a year in the future, people aren't really that bothered if you're out by a little bit each day. So the daily error doesn't necessarily tell us very much. Instead, we have 7-day, 30-day, and 365-day. So for these, we are just aggregating the results. So the 7-day error would be the total sessions across 7 days. The 30-day error would be the total sessions across 30 days. And then it works the same way as with the 1-day error, where we calculate the difference between the forecast total and the and the actual value. So generally, these errors, particularly they're on a different scale. So obviously, every 7 days you get more sessions than you do over 1 day. So these errors are bigger, but the percentage error, you can see it getting better and better, and that's because when you think about adding up over longer periods, you get the same effect as we see here, where positive and negative errors can cancel each other out. So the longer periods, you would expect the percentage error to go down. And this tells us that if we add up all the numbers for the year, we'd expect our totals to be, less than 10% out in the future, which is pretty cool to be able to get these estimates. Now, to do this, you do need to have enough historical data compared to the length of the forecast that you can make that you can look back and do it. For example, if you have 2 years worth of data and you're trying to forecast a year into the future, to get this estimate, you would have to exclude a year's worth of your data and make the forecast of only 1 year and then compare that against your actuals, which isn't good because if you only have 2 years of data, then it's very hard to learn things around annual seasonality. So you need enough data, enough historical data compared to the length of the forecast for it to be able to do this cross-validation. But all that's figured out manually. Sorry, all that's figured out automatically on the back end. So sometimes you'll see a result here saying, sorry, we can't do the cross-validation to estimate your accuracy. Other times you'll see a table like this. If your forecast doesn't go far enough ahead into the future, you'll see it missing. These rows will be missing. So for example, if you're only forecasting 2 weeks ahead, you won't see the 30-day or the 365-day rows. Okay, well that's it for this week's folks. I hope you've enjoyed the video, and as ever, just hit me up if you have any questions.